Okay, so here's another type of problem. We've done minimum perimeter, and then we did price change types of problems, and you have two of those in your MyMathLab for 11.6 day 2. And then this is a third kind. So this is still dealing with fencing and perimeter and area, but this time we're looking for the most economical fence to be built. In other words, we want to have a minimum cost. So sometimes you have to put the wording in a different format. So it says find dimensions that allow most economical fence to be built. So that would be the minimum cost. So here's the scenario. You have a fence and it encloses a rectangular area of 800 feet. The fence along 3 sides will cost $7 a foot, and the 4th side will be a different material that costs $21 a foot. And then find the dimensions that allows most economical fence to be built. So when you think this through logically, you have 4 sides. 3 out of the 4 will be built with material that's cheaper. The 4th side is going to be built with more expensive materials. So logically, you want one of the shorter sides to be the 21 feet. So we're going to put 21 on one of the widths, and then 7 is going to be on the 2 lengths and then on the other width. Okay, so the shortest side, or one of the shortest sides, has the most expensive, and then the 2 long sides and the other short side also has the 7 foot or the cheaper material. Okay, so here's the setup. We want the least cost. Well, when you think about it, cost is going to be determined by the perimeter. Okay, so the shorter or the minimum perimeter will give you the minimum cost. Okay, so here we go. We have our objective. So our objective is the cost, which is also the perimeter. Okay, so we want to minimize the perimeter, which means we're going to minimize the cost. Well, because we're dealing with cost, it's going to cost $21 per foot. So our width is going to be 21 times whatever the width is. So if our width is 2 feet, the cost is going to be 21 times 2. If our width is 7 feet, the cost is going to be 21 times 7. So we have 21 on the width, plus 7 on the length, plus another 7 on the length, plus another 7 on the width. So really all we're doing is we're just adding up the perimeter based on the cost of each side. And now we are going to add like terms. So our perimeter is going to be 21 plus 7, which is 28 width, plus 14 length. Okay, that is our objective. We want to minimize the perimeter or minimize the cost. The constraint is our 800 feet. Well, our 800 feet, should have been a squared here, is area. So we have a limit of 800 feet in area. So area is length times width equals 800. We always solve our constraint for one of our variables, and in this case, I'm going to solve it for L. I just chose one, that's all. There was no rhyme or reason why, I just chose one. So the constraint is L equals 800 times W. And like we did with minimum perimeter on the first equation, when you set this to greater than or equal to 0 to find our endpoints, what we find is if I multiply both sides by W, I get 800 is greater than or equal to 0, which is a true statement, okay? But because of how area can be manipulated, so for instance, I could have, 4 times 200, or I could have 1 times 800. There's really an infinite amount of combinations to get 800. So the limitations of 800 square feet, all we need to know is that our width has to be less than or equal to 800. So it's got to be somewhere between 0 and 800, or 0 and 800. Okay? All right, so we have our objective, we have our constraint. Our constraint is solved for a variable. We know that our endpoints are between 0 and 800. Now we're going to plug our constraint into our objective function, and this is going to be written in terms of W. So we have 28W plus 14 times 800W and we get P of W equals 28W plus 14 times 800 is 11,200 divided by W, or our objective is 28W plus 11,200 W to the negative 1. Okay? So our constraint is right here. That will help us find L once we find W. And now we can find the derivative. So the derivative of our perimeter is 28 minus 11,200 W to the negative 2. So remember, we're subtracting 1. That's where we get the negative 2. Now we're going to set this to equal to 0 and then solve. So I'm going to subtract off 28. Divide by 11,200, a negative 11,200. And need to get rid of some of this. And I get W to the negative 2 equals 28 over 11,200 is 0.0025. So in this case, all I did is I just divided 28 divided by 11,200, and that's the value that I got. You don't have to keep it as a fraction. I wanted to do one as a decimal so that since we're dealing with distances, you could see it. So 28 divided by 11,200 is 0.0025. Okay, so now I'm trying to get this by itself. So I'm going to raise it to the negative 1/2. Negative 1/2 times negative 2 is 1. Whatever I do to one side, I've got to do to the other. So if I raise this to the negative 0.5, I get W equals 20. Okay, so we're saying our width is 20. All right, so now I can plug it back in. Don't really need the endpoints, because the endpoints, calculating the endpoints just gives me zeros on either end. So if I plug 20 into here, my length is 800 divided by 20, which is 40. So the dimensions that allow the most economical fence is 40 by 20. This is my length, this is my width. Okay. Now, if you want to check it, you can find, for instance, if the question was what was the minimum cost, you could just do, you had the original, so I had 21 times 20, because that's the width, plus 7 times 40, plus 7 times 40, plus 7 times 20. So 21 times 20 is 420. Plus 28, or 280, plus another 280, plus another 140. So when you add those up, the cost is $1,120. So for this particular one, I didn't ask for I didn't ask for the cost, I just asked for the dimensions. But if that came up, you could just plug your value into here for width and length and find what the minimum cost is.